Hi, I'm Teacher Thomas. Welcome to A-Level Mathematics. This is the specimen paper for 9231 Further Mechanics for the 2020 exam series, question 1. A child's toy consists of a uniform solid circular cone, a vertical height 3r and radius r, and a uniform solid hemisphere of radius r. The circular bases of the cone and the hemisphere are joined together so that they coincide. The cone and the hemisphere are made of the same material. Show that the center of mass of the toy is at a distance 27/10 r from the vertex of the cone. I'll start with a sketch based on the description. We have a hemisphere and a cone, both with the same radius connecting the two circular faces. I can mark in some measurements. Radius is given as r. The vertical height of the cone is 3r, so I've laid that on its side. I'll show that length, 3r. Before I do any calculations, I want to check for two particulars about this question. First is density. I see the comment, same material. That tells me that both the hemisphere and the cone are the same density. I don't need to make an adjustment in my calculation for different densities. The next observation I want to make is I'm looking for a distance from where? The vertex of the cone. So let me mark that in pink. And that distance would be going right some distance. As opposed to starting, sometimes we might be asked to start from the far end of the hemisphere or from the circle where the two shapes meet. So I want to know where my starting point is for my distance calculation. I need to work with the concept of center of mass, so I'll begin by finding the mass of each object and sum them. First, the hemisphere. Mass of the hemisphere is 1/2 of the mass of a sphere. The sphere volume formula, as well as the cone volume formula, are given in the pure mathematics section of the MF19 if you want those. Okay, sphere is 4/3 pi r cubed. I'll leave it as that. R in this example is r. The radius is given as r. And for the mass of the cone, we went 1/3 times the height times pi r squared. Again, I'll leave the r as r. I'm going to change the height because in this example, the height, I have my cone laid sideways, so it's that horizontal length of 3r. That's the height of the cone. So I'll take out that general term and put in the particular term for our example of 3r. And I can sum these to find my total mass. The hemisphere, 1/2 times 4/3 is 2/3 pi r cubed, plus 1/3 times 3 is 1. R times r squared is r cubed, plus pi r cubed equals 5/3 pi r cubed. Now I'm going to address center of mass, and I'll note in my diagram center of mass location based on the MF19. These are coming from the mechanics section of the MF19. For a hemisphere, starting from the cone, actually. Since our starting point is the vertex of the cone, let's start there. From the vertex is 3/4 of the height. If you were working with a question that asked you to find the center from the base, then you would want to use 1/4 height starting from the base. As the formula is given, it's from the vertex. We're going from the vertex, so we use it as is, 3/4 h. For the hemisphere, starting from the base, we have 3/8 times height. Notice in this example we're not starting from the base, so we're going to think about the center of the hemisphere relative to the vertex of the cone. That's actually going to be the height of the cone, which is 3r, plus the 3/8 h. So when we work with the distance relating to the center of mass of the hemisphere relative to where we're starting, we need to add the entire height of the cone in that calculation. And for clarification purposes, we're going to be working with individual masses. So let me down on the left go ahead and simplify those two masses as I'll be working with them. So 1/2 times 4/3 is 2 over 3 pi r cubed. And then 1/3 times 3 is 1 pi r cubed. Those are the individual masses I'll work with in my following calculations. Step by step, or part by part, I'm going to multiply the center of mass formula for the cone. So I have 3 over 4 times h. Okay, that's over on the left. I've shown that in my diagram. And again, I'm going to take that h out and replace it with the actual height, 3r. So 3/4 of 3r, I'm multiplying, but just so I don't need the brackets, but to highlight that that's kind of a unit, I'll put that in brackets. I'm going to multiply by the mass of the cone, pi r cubed. Okay, put a check mark next to that down at the bottom, the middle pink row. Then I want to add to that. Okay, by adding, I'm increasing the distance from the vertex. The hemisphere is going farther from the vertex, so I'll add to that. And now, starting with the distance, we determined the combined distance is 3r plus 3 over 8h, that I definitely need in brackets. Okay, going up to the top left of the screen, a check there. That came from the hemisphere center of mass rule, plus the distance from our starting point to the base of the hemisphere. I'm going to multiply that by the mass of the hemisphere. We calculated as 2/3 pi r cubed. Okay, checking that down at the bottom. And this equates to the total mass, 5 over 3 pi r cubed, checking that down very bottom of the left-hand side, times bar x. And when we solve for bar x, that's the solution to this problem. First term on the left, 3/4 times 3, 9 over 4 pi r to the power of 4, plus, I see I left a general term. That h I can change. Let's do this in red. So I'm going to go back a ways and change this where I would originally want to have changed it. That's over on the left, where we have 3/8 h. The particular h in this case is r. And then at the top, 3r plus 3/8 h. That's 3r plus 3/8 r. And so the same thing's going to happen. I'll update my formula, my equation on the right side. That 3/8 h will become 3/8 r. And now let's continue. We can combine 3r plus 3/8 r will give me 27 over 8. And then times 2 over 3. R in each of the terms in the brackets times r cubed will give me r to the power of 4. Oh, I'll put the pi in front of that. Equals, I'll set this to bar x and divide on the left by 5/3 pi r cubed. This will simplify to 9 over 2 pi r to the power of 4 over 5 over 3 pi r to the power of 3 equals bar x, and the pi's cancel. Notice that we have 1 r remaining in our final answer, and when we take 9 over 2 divided by 5 over 3, the result is 27 over 10. Looking up at the requirement, show that the center of mass of the toy is at a distance 27 over 10 r from the vertex of the cone, is what we've done. This completes the requirements for question 1.